Right. First of all, thanks to give me an opportunity to come and present and share the experiences that we have had with running blockchain in production for last year or so. Um, I'll share my screen so that you can see the slide and we'll get going. Right. So about me, my name is Jatin Bhadra. I am based in Vakt's London office. We do have an office in Lisbon as well, and we'll come to that. I joined Vakt very early on, a year and a half back, when the system was still getting developed, and we were not yet live. And we took system live in around 6 months with our first release into the first market, and then we are still continuing to develop for the next market, and we have a release coming up very soon in next month or so. Um, so Vakt is based out of London, but we have an office in Lisbon, and that office we have started around 6 8 months back. And we have a very good DevOps team who works out of our Lisbon office and have been instrumental in taking the system live and continually running the system and facing some of the challenges. And we work together to make the system better every day. So, quick history about Vakt, what it is. So, the way in which I have structured the whole presentation is I'll give you an introduction, quick introduction to what the company is, what do we do, why we use blockchain, how we got to the blockchain, what is the architecture that sits over and around the blockchain infrastructure, and then some of the challenges that we have faced and how we resolve those challenges. So the company was started around maybe around 2 years ago, and it took around 6 months or so in the ideation phase. Essentially, the company's purpose was that it was started by these oil majors. So all these oil traders, which you can see over here, in energy traders, the big oil companies like BP, Shell, etc. They continuously buy and sell oil from each other, and they had a problem in their business area where the process of buying and selling oil was all offline. So the traders would call each other, they'll agree on the trades, and then they'll pass this process on to their operators, who would then go and enter data into their individual systems. But there was never any central reconciliation platform. So typically, you would think that that kind of system would have been developed years back using database, but that was not an option for these companies because they are very secretive in terms of the information that is shared in that trade. Yeah, the trades are very, the frequency of trades, all that matters quite a lot. And you can see right now with the oil prices going up and down, etc. So they are very precious about their data. They don't want any other company, any other central body to be having that data. So having a central system was not a solution to them for them. So this problem existed for them for years. And in came blockchain distributed ledger technology. And that is where they thought that, okay, distributed ledger technology allows each of these companies to have their own data, but still share the data in a secure fashion so that there is a source of truth where this can be recorded. And hence, they started us, that is Vakt. So there are around six trading companies, that is oil companies that explore oil. So they have their own oil, and they trade with each other, guys like BP, Shell, Chevron. And then there are three trading companies. So these companies typically don't have their own exploratory oil. They basically just buy and sell in the market, and banks. So that's how we started. And in terms of business, a quick overview. Uh, this is important to know. This will come back to the architecture. We don't. We are not futures trading. So we are not one of those fast, high frequency style platform that you typically hear of when in IT we talk about trading. Uh, we are solving the physical trade problem. So in a way, from technology perspective, we have the luxury that we don't have to deal with a large volume of transaction, like high frequency style transaction. Plus, our platform doesn't get involved into trading aspects. What it's very good at is all the communication that happens post trading. Again, over here, this point about the communication that happens post trading is important, because that is how we will go into the architecture and then into the implementation of how we provide these companies a secure channel of communication using blockchain. So on the left hand side, the trade, and on the right hand side, settlement. Settlement is where you deal with the real money, is something that we don't get involved in, but we do get involved in everything in middle, which is when the two companies have agreed on the trade, they come onto our platform and they can see both sides of the trade, so that they are absolutely sure that both the parties have got the details correct. They can agree on the trade, and then they can share the logistic information on the trade. That means which ship is going to now actually physically carry the oil from one port to another port, where the port will be, who is the terminal. So all that communication happens on our platform, and our platform is good at doing that. So a quick overview of these are the kind of customers that we work with. All of these are small to large enterprises. And again, we will touch into why it matters, because we have to provide them with enterprise grade SLA and how we achieve that using cloud technology. Right. So how does Vakt work then? So we talked about the problem that we started with. The problem is that these companies wanted a secure platform, a platform where there is no central ownership of data, a platform where they can trust that the information that has got in from the source, and the trust that once the information has got in, it is not manipulated. So that is where the distributed ledger technology using blockchain comes in. As probably most of us know, is once the record is written onto blockchain, it's immutable. It cannot be muted. It's tamper evident. If there is an attempt made to tamper with the record that is on blockchain, then the blockchain network, with its consensus algorithms, will reject that kind of attempt to tamper. So that is where the communication comes in. So all the communication that happens, that we facilitate, is using blockchain. So once it's written on the blockchain, it cannot be amended, as in it cannot be tampered with. Obviously, for business reasons, there will be a reason to amend if a record that was written was erroneously written wrong. Then the business process allows a further record to be written onto the blockchain, which corrects the record that was written previously. But always there is the history of what was written, and then from business process perspective, what was changed. So the records are always immutable and they are tamper evident. Second aspect, which we talked about, typically, if you use the blockchain network, in our case, right, let's come. Typically, when you use blockchain network, like Ethereum blockchain network or Bitcoin, the ledger that sits under it is publicly available. So anyone can participate into the network. All the data is available to everyone who is participating in the network, because that's how the distributed ledger technology works, right? Everyone has got the full copy of ledger. However, the requirement that we have is that we cannot have the full ledger distributed to all the participants in the network. Plus, the network has to be protected so that only the participants who are authorized to be in the network are allowed to be in the network. So that is where the private transaction and the permission blockchain node comes in, and we'll come on to the next slide of the technology that we use to achieve that. The third key point is all that we do is highly scalable, secure, with no data loss and a good disaster recovery, and that is where we use the good practices of cloud technology to achieve that. Now, this is the most interesting slide from architecture perspective. Let's so when we provide our customers. So the solution that we provide to our customers is each customer gets a blockchain node. We provision the blockchain node, we support the blockchain node, we maintain the blockchain node, we upgrade the blockchain node for our customers. However, to access the blockchain node, we obviously write a layer of API, which is written in Java. So over here on this slide, you can see the Quorum is the technology that we use. So this is a JP Morgan Quorum, which is built on top of Ethereum that provides a privacy enclave around the public Ethereum technology. So Quorum is the technology that we use. That's the underlying foundation on which all the records are kept. To access Quorum, we provide a layer of API that is written in Java. And there are two consumers that we cater for. One is the human operator in our customer's organization. So for them, we have a React front end using which they can record the transactions through the API onto Quorum. However, we prefer our customers to not have that human interface, but to actually enter data into their systems and integrate their systems into the blockchain node that we have provided through messaging infrastructure. We do have REST API as well and messaging API through which they can connect their systems into. And then for identity access management, we provide Keycloak, and then there is a bunch of peripheral services to provide good monitoring, to provide a logging infrastructure for our internal support and developers, and secret management to keep our blockchain nodes keys secure. And we'll do a slight deep dive into how we do that. So this is what a combination of this makes one running system that each customer gets. So customer A, when they say, hey, Vakt, you are cool, we want to use you, then we bundle this whole thing up and we deploy it for them. And that bundle we call as a pod. So over here, there are pods that is for one customer, second customer, third customer. And all these pods then are able to communicate with each other over blockchain network. So you can see all the crisscross wiring happening, all the pods being able to communicate with each other. That is all communication happening over Quorum technology, that is blockchain technology, allowing a secure communication happening from pod to pod. That means that when a customer in this pod wants to have a transaction with a customer over this pod, then the data that is exchanged is between these two pods over this communication channel, which is over Quorum. Now, with our guarantee and with our assurance, we as a company do not participate in blockchain network. We don't have a blockchain node that is Vakt's blockchain node. We provide blockchain nodes to our customers, but we don't participate because we don't have any legitimate need or a reason to participate on blockchain network. We do have a central services pod, which allows us to distribute some central maintenance type services like updates to reference data, or allow the customers to share some documents. So when customers want to share documents with each other, they generally keep it on this dark gray circle that is sitting over here in this architecture. So we went through this, but just to reiterate, the key aspect over here is there is a Quorum node. To access Quorum node, we provide API. To access the API, we provide a React front end, and we provide a layer of messaging that allows the companies to have system integration. And then we provide the identity management system and monitoring, logging, and some secret management. And we'll touch a little bit more deeper into the monitoring aspects of how we use Prometheus and Grafana for Quorum monitoring. This is giving a bit of a deep dive into what do we do in the central services database, central services pod, which is distribute the reference data that is required to be shared across all the pods. Now, there is another thing that happens over here. Because all these pods are sitting and are running by themselves, there is a lot of information or shall I say configuration that these pods need to distribute. That is an IP address on which one quorum node is running. That quorum node needs to publish its own IP address to all others, and all others need to then do the same with itself. So it needs to whitelist everybody else's IP address and vice versa. So all that kind of information, that I would say, again, rephrase, configuration that is required to be shared across the network is also something that we maintain on this central pod. So as part of our provisioning process, whenever provisioning is done, a new participant or a new pod that comes onto the network can publish its own configuration and can get everybody else's configuration so that that pod can successfully connect into the network. And that is all done by our automation process. That is all done by our CI/CD process, which we'll touch onto as well. So, little bit of cloud over here, with the assurance that we give our customers that their network, their pod is completely isolated from anybody else's pod. How we do that is for every customer, we run their pod in their dedicated AWS account. Again, in their AWS account, there is a VPC. Within their VPC, there is a subnet infrastructure. So that's one account, one customer, and so on and so forth. So we do, in some cases, optimize the use of AWS accounts. So typically, most of our big customers, they prefer this kind of architecture where they get their own AWS accounts, their own VPCs, and they have got absolute guarantee that their network is completely isolated from anybody else's network. However, we do have what we call as a multi-tenanted, or if you think as a light pod, where we don't necessarily create a fully dedicated AWS account for each customer, but we use a multi-tenancy concept, and we'll touch on to those. But essentially, what that gives us is it gives us a cheaper AWS run cost, and hence that allows us to give a slightly advantageous pricing point to those customers who prefer not to have a fully dedicated setup for them. So this is what happens in case of a single use. So when a customer says that, hey, I just want complete isolation, I want my own setup, and I don't want to share my setup with anyone, we build a AWS account. In that AWS account, we build them a quorum node. Most of our customers don't just have one legal entity, they have multiple legal entities in their organization, and they want to transact within the legal entities as well. So again, if they are transacting from one legal entity to another legal entity, that means that they both need a quorum node so that they can share the transaction data between themselves. In this kind of setup, we can have a organization, one AWS account, and each legal entity in that organization has got its own blockchain node, that is their own quorum node. But they then share the same API layer, they share the same messaging layer, they share the same identity layer, because essentially the companies want a single sign-on functionality going from their infrastructure onto the pod, and this allows them the flexibility of signing in once, but then acting on behalf of any legal entity within that organization that is from their operator's perspective. And same applies for data as well. Coming to a light version of the same. So when we say a light version of same over here, you can see rather than having legal entity at organization at quorum level, this is organization at quorum level. That means we still give each organization their own quorum node. So this could be some small companies or some medium-sized companies or even big companies that don't have too many transactions in any particular market and would prefer to get a lighter version of our pod. Then this is what they can have. They can still be assured 100% that they are data is secure and is isolated physically from anybody else's by having a dedicated quorum node. But over the top, they share the layer of API. And coming to the key cloak layer or AMQP layer, they, from infrastructure perspective, they are sharing a cluster. They are not getting their own dedicated infrastructure, but within that, using the technology that RabbitMQ in this case and Keycloak, they get logical separation. So still they are secure. Still, it's not as if the organization one can see the data of organization two. Each organization has got their own security. However, they don't have the full physical security that one gets in the setup of a single use pod that we talked about. Okay, let's jump slightly into what does it mean from cloud infrastructure perspective. So for every customer, we provide at least two environments. Remember, these customers, they obviously want a test system and a production system because they work with us. They integrate their IT into our pods, or shall I say, their pods that we run for them. So they have a test and a production, which we call as a preview and a production. So each get two AWS accounts, and they have their preview running in one account and their production running in another account, and we then propagate the code through those accounts as part of our release process. The communication that happens across the pods, the quorum communication that we talked about, because these networks are completely isolated, so there is one VPC sitting in one AWS account, and then there's another VPC sitting in another AWS account. The communication that needs to happen, the quorum, the blockchain level communication that needs to happen between these two completely separate AWS VPCs have to go over internet. We could have, probably unlikely that it works, is have VPC peering across all the AWS accounts, but that would have created a very complex VPC peering network, because every VPC would have had to have VPC peering going into every other VPC. And for those who are familiar with the VPC peering concept, in that kind of situation, you need each of these virtual networks to be running with its own, with non-overlapping IP range. So management of IP range and configuration of the various VPC peerings, and then potentially even hitting AWS hard limits of maximum number of VPC peerings that are possible. So that was not the solution. Hence, this idea of going out and then coming back in it works very well for us, and we have been running with this for some time. So one of the concepts of blockchain nodes would be that if a company has a blockchain node and they want that their data is secure and cannot be tampered with, and they want 100% guarantee of that, one would argue that they should probably run the blockchain node in their infrastructure and not let us manage their blockchain nodes for them. Now, as being agile with the regular release cycles, etc., it's of a significant advantage if we manage the blockchain nodes and the pods for all the customers that we have, because then that allows us to move at a very rapid pace, do regular releases. Being on blockchain means there are a number of things that need to be aligned when you do a release, as such. Smart contracts, as such, the version of blockchain nodes that you are running. So the version of quorum node that you are running all needs to be aligned as part of a release process. When it's upgraded, when a smart contract is upgraded, you have to upgrade all the smart contracts across the network. So it's important for us to be able to run that. But at the same time, we want to give assurances to our customers that their blockchain node, their data is secure, and we don't have permission to read that data. and how do we audit that kind of information. So that is what I'm trying to show on this slide. So bear with me. I'll probably go slightly into AWS terminology, but I'll keep it as simple as possible. So what's the crown jewel over here? What do we need to protect? Two things. One is the quorum private key. That's the private key that is used by quorum to encrypt the transactions. And second is the data that is residing on that quorum node. So we'll talk about quorum key. So how do we protect that quorum key from using our processes? So the generation of the quorum key is automated as part of our CI process. So the CI server sitting over here generates the quorum key and then stores the quorum key onto an S3 store. This S3 store is then encrypted using AWS's key, which is kept in AWS service called as KMS. So the only permission to decrypt that S3 location is provided to the quorum node that is running for the customer. So only customer's quorum node can use the second key that we have generated on AWS and hence decrypt the first key that is sitting on S3 to be able to use to encrypt the transaction. CI server that has provisioned that key has got permission to create the key, has got permission to delete the key, but hasn't got the permission to decrypt that store. The only service that has got permission to decrypt that store is the quorum node service that runs in our infrastructure. Also, because AWS's service KMS is used, KMS comes with inbuilt CloudTrail, which is Amazon's auditing mechanism, and it keeps all the audit records of what has happened with this key, who used the key for what, as in was this key decrypted, was this key encrypted. So that allows us to gather the full history of what was done to that particular key. And that's the mechanism that we use. Because this CloudTrail log is collected by Amazon, we don't have any control over it. We just ensure that this is enabled. That gives us, our customers, assurance that their data, their key is secure in our infrastructure. In terms of monitoring, there are lots of moving parts over here, as you saw in the infrastructure. We'll touch over two aspects of monitoring that we do onto the for our customers. So the central services pod that we talked about, that was what was used to distribute reference data. That same pod is used also to monitor what is happening and what is the service status of these pods. So we use the combination of Prometheus and Grafana for monitoring. So let's talk about Quorum. So Quorum that runs in each of these AWS accounts, we deploy alongside Quorum as a Docker sidecar, a Quorum exporter. This Quorum exporter exposes some of the key metrics of Quorum. And one of the important metrics that we monitor is the peer count. That means how many nodes is this particular quorum node seeing in the network. And we gather that from every quorum node. And that is what we use to monitor the state of our or health of our network. If any quorum node fails to communicate with another quorum node, when we expect it to be communicating, that is during our normal runtime operation, then that raises a Grafana alert that goes to our support team. And with blockchain being, shall I say, evolving technology, it's come in very handy as part of our run activity. We have had a version of Quorum running in production for months, and it was very stable. And overnight, we started to see some instability creep into the network with no underlying change to the Quorum version or any significant changes in transaction volumes or any data store or any memory usage. But this was very useful for us, that we were monitoring the quorum network, because it was just a pretty random failure. We got a fix on that, and that was applied. But at the same time, recently we discovered that there is another service that we were failing to monitor. So the way in which Quorum network, the blockchain network over here works, is there are three services that all need to communicate with each other. Underlining, there is Ethereum service that needs to communicate with each other, and then there is a total network count of how many Ethereum nodes can see each other. On top of Ethereum, Quorum has got a privacy layer, which is a Tessera, which is written in Java, and that also communicates with each other. We were failing to monitor the Tessera level health network count, and we just recently added that feature, and that did bite us with one issue where because we were not monitoring it, we had to see some failures in our service. So now, having this exporter and having the flexibility of Prometheus and Grafana allowed us to pretty rapidly upgrade our Quorum network exporter, Quorum Prometheus exporter, to add the extra feature of Tessera monitoring as well. The second key aspect of monitoring over here is CloudWatch. So CloudWatch is the service with AWS that gathers the logs and also exposes some of the key underlying AWS service metrics like memory usage, CPU usage, etc. So that's the second piece that we monitor. So we have got CloudWatch exporters, which run in the central service, because they can remotely extract the metrics from the AWS service. So this is slightly different. Quorum, the CloudWatch exporters run in the central service, and they simply remotely extract from AWS some key metrics and provide it to Prometheus, and then we have got a bunch of Grafana dashboards and alerts that come out of it. And over there, we monitor one of the simplest thing that I can talk about that we monitor is how the expected number of EC2 services that we want to be running in any particular pod. I'll slightly rewind that all that we run, everything that we run runs in Docker. We use ECS to orchestrate our Docker containers. We don't, well, there was some argument, some debate about whether we should use Kubernetes. Currently, our feeling is that our setup is kind of strange, because we have got these pods, which are self-contained units, and we need to deploy these self-contained units n number of times. If we start to add a layer of Kubernetes in this self-contained unit, then we probably will increase the complexity of our setup, because now we not only this unit, but along with this, we have to continuously deploy Kubernetes infrastructure as well. So right now we are staying slightly away from going Kubernetes way. Let's talk about CI/CD stack that we started with, and then how we have evolved over last a few months from using that CI/CD stack. So our initial CI/CD stack that we started with was Concourse, and then with Concourse we had a bit of a layer of shell code and rake, so Ruby rake. So the rake was the layer along with a lot of shell scripts, and then we used to call Ruby, and Ruby used to call Terraform. So the challenge that we had with that stack was that with Concourse, we found that the knowledge in the team and generally the knowledge in the industry was not that great. We struggled a lot trying to get Concourse to do what we wanted, and that's probably there are twofold reasons. One is the comfort level and the knowledge level with Concourse was not that high. And also Concourse as a tool is very strongly opinionated in terms of how it can be used. At the same time, we found that the way in which Concourse spins up all the underlining Docker infrastructure or container infrastructure, to be precise, not Docker, is resulted in Concourse running fairly slow from time to time. The other problem that we had with Concourse was that the flexibility that we wanted with branch detection and then spinning up the new pipelines using branch was not that great. And again, going back to the Docker support, we struggled quite a lot to use some of the very basic Docker features that we wanted from Concourse. That was not trivial to implement. There are some advantages of using Concourse, I guess. The support for pipelines and pipeline stages, and then hooking up and wiring the pipeline stages is neat. It has got a very good user interface that allows you to get a very good view of all the pipelines. So there were a couple of advantages as well, and also the way in which pipelines are built up of stages allows you to replace some of the stages or start from some of the stages. So that was some of the advantages that Concourse had. But the advantages that we saw with Concourse and also having a full-blown programming language like Ruby in our CI setup. Was just too much there were just too much complexities. And again, having a language like Ruby probably is a significant advantage, but at the same time, because of that, we found that there was just layers of complex code which doesn't go very well in our belief with the model of infrastructure as code, where infrastructure of code is generally like, this is the state that you want, it is idempotent code, and it just does what it says. Whereas with having a full-blown programming language, right, Ruby, that was giving a lot of loose ends to that principle. So when we decided that we need to move off that CI stack onto another CI stack, we put and we agreed, we set some basic principles of what we want and what we don't want. So the first step was that at the top layer, the layer that over there is a rake layer or a shell script layer, we want that layer to be very simple. There should be no logic, and it should just be a layer that allows you to invoke the underlying commands very easily. So makefile it was selected, and makefile, the principle of the makefile that we did, which is no logic in makefile. The makefile is essentially a wrapper file that just gives you a very easy interface down to the underlying tool that is used. So think of make layer, the top layer, as an interface layer. The second layer is the layer that is the orchestration layer. And Ansible is what we selected for orchestration layer. And this orchestration layer is that allows you to then run your cloud infrastructure provisioning or your infrastructure provisioning in the right order that you need to run it in. For example, creating a VPC first, creating ECS clusters first, deploying services in that ECS cluster. So those are the order in which you want your infrastructure provisioning to run. So that is the job of Ansible. Alongside that, rewind a bit. So when I talk about infrastructure provisioning, Ansible's job over here is just to do the orchestration. Ansible's job is not to actually do the cloud automation. The cloud automation, the invoking of cloud APIs to actually provision those services in cloud, that is what, in our case, is role of Terraform. So it's clear that we went with if you can see over here, it's not as if one tool, we should use only one tool and do everything using one tool. Just select the right tool for the job and then keep the tool confined to the job that it's selected for, and try very hard not to not to kind of slip into a like Ansible can do cloud automation, so why not just do a little bit more cloud automation in Ansible rather than Terraform? Now, these are the principles, right? These are not rules. So there would be a good use case, which in our case there is in some places where Ansible is used for some cloud automation, but basic guidelines, basic principle is very clear. Makefile, a simple interface, Ansible for orchestration, and then Terraform for cloud automation. In addition, what Ansible was in very good at, what Ansible was actually started as was a configuration management tool. So the services like Keycloak, the services like database configuration, all that kind of configuration that Ansible is actually very, very good at. We use Ansible for that as well. So all the role provisionals that we need to do in Keycloak, all the RabbitMQ configuration that we need to do, all that kind of stuff is sitting in Ansible's domain for us. So as I said, the new CI stack, which is Jenkins, Make, Ansible, and Terraform. So we talked about Make and Ansible quite a bit. We didn't talk about Jenkins. So over here, comparing Concourse and Jenkins, what we gained by moving off Concourse and moving to Jenkins is we use Jenkins multi-branch pipelines. So that allows us very easy branch detection. All the pipelines that we have are multi-branch pipelines. So when a developer wants to create a test environment using their feature branches, it's very easy for a developer to start the process of provisioning the infrastructure. Same way, when we come to some other test environments where certain deployments may be required from some short-lived or sometimes some sort of release branch, then that can also be facilitated quite easily using the Jenkins multi-branch pipeline feature. Again, over here with infrastructure as code and with the principle of everything should be code, we use Jenkins pipelines to full. So everything that we do is sitting in Jenkins pipelines. We just point it to the pipeline, and Jenkins pipeline then invokes the make a layer to then further invoke the Ansible and Terraform layer. Another thing that is very important that we did very early on, and we are continuing to do that, is whatever runs on Jenkins, it runs through pipelines in Docker, which means that whatever runs on Jenkins as an infrastructure developer or as a DevOps engineer or as a developer, I should be able to run exactly same on my own machine without having to do anything extra. So what sits in Jenkins pipeline has to be as simple as possible. There shouldn't be conditional code. There shouldn't be logic in infrastructure in Jenkins pipeline that you cannot run from your local machine. So we have very broadly defined scopes. So there are layers of infrastructure that are provisioned once per account. There are layers of infrastructure that are provisioned per environment. So all that are very clearly defined in the pipeline at Ansible level, at Terraform level, and then Jenkins pipeline just simply invokes those scopes in order to create a running infrastructure. The other advantage of using Jenkins was Jenkins native Docker support helped us quite a lot. As I mentioned, everything that we run as Docker service. So as part of our build pipeline and then as part of our provisioning, that is deploy pipeline, in the build pipeline, we have got quite a few Docker images that need to be built. And by having native Docker support and hence having a native Docker cache support on the Jenkins slave infrastructure allowed us to speed up the Docker image build process quite a bit. So just reiterating these principles, probably I've covered all of this, so I won't go through these again. So just this is a screen capture that I took recently from our Jenkins pipeline in terms of how we use the nested parallel feature of Jenkins. So over here, There are a bunch of images that have been built. I have not captured that part over here. But once the images are built, this is from one of our test environments. So this test environment essentially has got 5 different AWS accounts on which it has to start to provision the pod. So what we do is we start Jenkins running in parallel, and it goes across and invokes the Ansible and Terraform code to provision the pods in 5 different AWS accounts all at the same time. So then there are various stages that I talked about. So there is a stage where it provisions network, then some of the clusters, databases, and so on and so forth. It goes until it comes to this point where it starts to run some of the basic, if you like, infrastructure level smoke tests and also health checks to see that all the services that have been provisioned as part of this setup are successfully running. And then it moves on to invoking automated test suites that actually test the application at using um, uh, Cucumber and some of the other frameworks to test at REST level and to test at UI level. So somewhere over here in the middle, it does a lot of quorum provisioning. Some of these stages that kind of are in small chunks are just to optimize the way in which stuff can be run in parallel. And some of these stages, the reason why they come back up and then go out are required as part of the quorum network provisioning. As I said before, once a node is provisioned, that node needs to then share the information with all the other nodes. So everything has to wait till all the quorum nodes have got to a state where they can now proceed to the next level. So hence, you can see this pipeline going out and coming back in and waiting for all the accounts to at least finish some activity before they can proceed to the next step. So there are some more challenges that we have faced. There are some challenges that we have resolved, and then there are some challenges that we are still working through. So as soon as you introduce a layer like distributed blockchain, distributed ledger technology onto the network, that this first point is about the complexity that comes with is. So in our architecture, the way in which the application, that is the API, discovers that there is some activity that has happened on quorum node and it has to perform an action. For example, when a trade was entered by participant A, which was with a trade with participant B, essentially at quorum level, there was action, there was a transaction that happened. And now API at B needs to listen for an event that is going to get emitted from the quorum node that's living underlying the B's quorum node. That event and the way in which that has been developed and the way in which all the race conditions needed to be handled, as it stands, unfortunately, our API layer is a singleton layer. That means we can run only one version or one kind of what's the right word? We can have only one instance of API running in production. From cloud perspective, from CI perspective, from cloud native application perspective, that's a complete anti-pattern. However, we are in that stage, and right now we haven't tackled that problem yet. One potential solution over there is at the quorum messaging layer, quorum event emission layer, to then have another layer of messaging that then allows the application API to run multiple instances. We haven't got there yet. That's still an outstanding issue, outstanding challenge for us. The second and third point, as I mentioned before, as soon as you introduce the layer of smart contract, and that smart contract is distributed across the network, from time to time, probably with company like ours, very early on, you need to make some business change adjustments to those smart contracts that have been written. Now, smart contracts are meant to be immutable. You cannot change it. However, for business reasons, there will be requirements to change it. And that is where the smart contract version management, the smart contract change management, and smart contract migration comes in, because you have business logic, you have state that is residing along with that smart contract. And if you change the smart contract, then you have to carefully make sure that the state that was in the old smart contract moves on to the new version of smart contract. So that we have simplified by keeping a fairly limited business context in our smart contracts, and manage it very delicately to ensure that we are getting best use of our smart contract layer, but at the same time not creating ourselves a big smart contract management overhead. So those are the second and third points that have been that are well managed right now. The third point, typical CI process, that every feature branch should have its own test environment, and a test environment should be easy to spin up, test environment should be cheaper to run, is all great. But we can't get full benefit of that because of the distributed nature of our architecture, which means even the simplest of test environments needs at least 3 pods. That means spinning up network in 3 accounts, installing all the other components that we talked about on those 3 accounts. So the run cost of keeping those accounts running is not cheap. And then you multiply that with number of developers, number of feature branches that they may have, and number of potential test environments that you need to support the QA team, increases the cloud cost significantly. As a team, we did a very good job over last 3 to 5 months to get that cloud cost under control. Slowly but gradually, we are getting there by a very good use of Amazon Spot instances that for lower environments, so that we have a significantly lower run cost of EC2 instances on which the ECS service runs. Uh, a good balance of nightly shutdowns. So we now have using Amazon's auto scaling group schedules. We shut down all of our test environments, most of our test environments overnight. However, the configuration control is over there in the branches. So if any team does prefer to have their environments running for whatever reasons overnight or over weekends, it's just a matter of making sure that the right flag is set in the configuration and it accordingly doesn't shut down. And the third point was RDS, which is the Amazon's database service, to shut that down every night. And you can see the order in which we are going. So these were the most costliest services in our infrastructure. That is EC2, RDS, and the third is load balancers. We haven't got to load balancers yet. Next on in our list is to start to overnight delete the load balancers and then provision it in the morning. Arguably, we would like to be in a position where we can actually destroy the whole setup every night and build the whole setup again. But it is time consuming. It takes a good hour and a half to provision full infrastructure, and at times it's not that reliable with various issues. Hence, we are taking step at a time to keep things in control, to keep costs in control, at the same time improve and get to that target state where we can delete everything overnight and then reprovision it in the morning. I think that was the last slide. So I think I've gone through everything that I wanted to share.
Well, thank you, Jatin. We will open up now for Q&A. So remember, there are 2 ways that you can place your questions. One is by raising your hand. Another is by placing questions in the chat. So if you have questions, please either do one of those actions. Okay, Manuel Pais has a question. Manuel, Go ahead.
Hi, thanks for the detailed presentation. I was wondering if it seems like you use a lot of AWS services. What about kind of the security aspects of blockchain? Was there any specific concerns that you had because of using blockchain, and how did you deal with those?
So in terms of keeping the blockchain secure, the two things that I would touch on. One is what I touched in detail on is the private key and how we keep that secure. And the second aspect is the network itself. How do we keep network secure so that the private network that we have built is private and we don't have rogue nodes on the internet trying to participate in the network that we have built. So Quorum as a technology comes with a concept that is called as permission nodes. So every Quorum node needs to know about who are the other permission node in the network. And only those nodes are then allowed to join the network. And it does that by a combination of those Quorum nodes' IP addresses and also by their public addresses. So that's the identification in the network of the Quorum node. So those are the two identifiers. That's how we keep it protected at, if you like, the protocol layer. So that's at the blockchain protocol level is the security. And then if you go down a layer that is at pure network layer, we use Amazon's security group, which is the firewall that sits around the machine and protects the machine's network from being exposed to unwanted attention, if you like. So that's another layer that we use to keep all these Quorum networks protected, so that only the IP addresses that are valid IP addresses can initiate a communication. So I talked about two things. So one is how we protect keep it all secure at network layer, and other is from the key layer and at data layer, that encryption key and the volume itself.
Any other questions? Go ahead, Marcel. You have a question?
Thank you. Oh, at first, thank you very much for the presentation. It was very nice. My concern is regarding how did you decided about the roles for Ansible and Terraform? Because we've got a lot of things that can be used for by both ones. So how you decided better which kind of functionality should be for each one?
So I think the basic principle is that by default, anything that is related to cloud. So Terraform, I will just use this example. Like Terraform started its life as cloud automation tool. Ansible started its life as configuration management, so that it can manage the configuration of the servers, and it has got very neat concept of playbook and rules. Both these tools then, as a second thought, that's my personal belief, right? Both these tools as a second thought then added other things. Like Ansible then, when cloud came in, it thought, okay, right, let's add a bit more support for cloud. So it was almost like an afterthought that, yes, Ansible is very good at doing configuration management, but now that cloud is around, we'll also support cloud, and we'll also have some features that you can automate cloud as well. And Terraform started with the idea of cloud automation as first thing, and then using other providers' concept, added more features to support initially with local exec and later on with the provider infrastructure that, yes, you can configure some other services as well. So that was like, Terraform does cloud automation very well. Ansible does configuration very well. Ansible does orchestration very well. So that's how first we separated out. Second, this idea of Terraform where you can you can run stuff in plan mode, which is what you don't get easily with Ansible. That how do you run stuff in plan mode to see what's actually going to happen to your cloud infrastructure? To get that in Ansible is not that simple. So that was another reason why we kept it pretty clear that this is Terraform, this is Ansible. Now, if you are familiar with Terraform, then there is like a seed thing, right? I mean, we keep remote state on S3. So sorry, everyone who is not native to Terraform, but when we need it to support Terraform, that is when we use Ansible. That if Terraform needs something to be available in cloud that it cannot do by itself because it needs that in first place, like the state location, that is when Ansible comes in and does that for Terraform, and then let Terraform continue the cloud automation.
Rodrigo, you have a question? I'm going to unmute you.
Hi, can you hear me?
Yes.
Okay, cool. I have a couple of questions actually. One is regarding the communication with your clients, the infrastructure. Do you actually do the integration when you use the API via internet itself, or do you usually actually something like direct connect to integrate with the clients? It's more an infrastructure question.
Yeah.
And the other one is regarding the reports. As you're saying, you use Prometheus and Grafana. Do you also make that available to your clients to see what's going on their own environments? That's it.
Okay. So the first question is yes, we do use internet for clients to communicate onto their pods. But in case of single-use pod setup, we do use a combination of Amazon's web access firewall and security groups to ensure that we are whitelisting our clients' IP addresses so that their communication is as secure as it can be. So we use all those best principles to make sure that although we are on internet, but our channels are restricted, and then all the communication goes over TLS so that it's all secure. Second point, not yet. It is our desire to provide clients access to the monitoring so that they can subscribe to these Prometheus channels. They can subscribe to the Elastic CloudWatch. They can ingest, is the right word, logs, and they can ingest the metrics that we are producing, and they can then also do monitoring at their end of their pods. So it is our desire to do that. It has not been done because in a way we are providing a managed service to our clients. So we really take that responsibility to ensure that our client's infrastructure is running all the time when it's supposed to run.
Any other question? Nope. No questions. Okay, I'm going to ask mine because I'm interested in knowing what's your plan in moving away from AWS. Are you and your clients all stick to AWS?
So we are using some AWS services for sure, but a lot of things that we have done runs in the containers and. For example, let's just take an example. We don't use SQS, we use RabbitMQ. We use Prometheus RDS, we use Postgres RDS, but that's Postgres underlining. We don't use Cognito, we use Keycloak. So we have tried not to tie ourselves fully from architecture perspective with AWS, with this desire from very early on that we should be able to run on any other cloud. We think at some point we will have to, because we are running the service for our clients. So at some point our client may ask us that they would rather prefer to run on another cloud provider, their pod, than on AWS. And we would then start to support that cloud as well. As of now, I think with all the engineering effort that we have put, we are happy running on AWS, and it has served us very well. But I think there will be a small application layer change if we have to move to another cloud provider. However, from DevOps perspective at Terraform layer, there will be quite a bit of engineering required. And that is where probably the argument of having a layer of Kubernetes could work, but still it seems like a lot of work to have that layer of Kubernetes just to get the cloud agnostic implementation. Because I see our run cost increasing significantly, having to run each pod in its own Kubernetes.
Okay, thank you.